As we've seen before, the flux is just the amount of something flowing through an area. Therefore, the magnetic flux is just the amount of magnetic field going through the area of interest. Magnetic flux can be described by this equation, where A represents an area vector describing the size of the area and some direction, and B describes the strength of that magnetic field. So we've said a couple of times now that current and moving charges actually create magnetic fields. Well, it turns out that the reverse is true. Magnetic fields can create current too. However, this only occurs if the flux through our loop of wire changes, and that's what Faraday's law describes. If there is a change in flux over time, we induce a potential. And if we induce a potential and we have some form of resistance, that means we induce a current. Now don't worry about this negative sign too much. Lenz's law is going to take care of that for you. So let's think about how we can change this flux over time to get this induced EMF. If we look back at this equation, we can change the area, we can change the magnetic field strength, or we could change the angle between the two. So if I change the area, I'll say, okay, maybe I'll expand it. That'll increase the flux and change it with respect to time. So I would get an EMF induced. Now I could also change B. Maybe I'll make it point left, maybe I'll make it point right, I'll flip it on and off. As long as B is changing with respect to time, the flux will change and will induce an EMF. So we can see an example right here. The final option is to just spin our loop of wire. So if we just continually turn it, we end up inducing different currents in different directions. As it turns out, that's how most generators work today, where you rotate a magnet around a loop of wire and you can actually see that current is produced in an alternating fashion.